Hello, BC Calculus folks. What I'm going to try to do today is I'm going to try to give you a quick little update on what we did on Thursday after school, dealing with L'Hospital's rule and relative rates of growth. In this short lesson, we're going to just talk about L'Hospital's rule, for those of you who may have missed it. And the first thing we want to talk about is what is an indeterminate form. After that, we want to talk about how you evaluate limits that have such a form. And in doing so, we'll be talking about L'Hospital's rule. So let's get underway here. So what is an indeterminate form? An indeterminate form is a form that when you evaluate a limit, you get the result of either 0 divided by 0, infinity divided by infinity. You might get 0 times infinity, infinity times 0. You may also get infinity minus infinity. All of these are forms that you may get 0 raised to 0 power or infinity raised to 0 power. These are all forms that you basically cannot say what the limit is heading to. It's called indeterminate. So we're going to deal with the first couple, and then we may work with a couple others with some examples to just show you how you navigate the waters for the different types of indeterminate forms. First thing is first, let's go back to a limit that we did earlier in the year. Let's say that we're going to approach 0, and we're going to try to understand what the sine of x divided by x is. If we try plugging in the limit, we get the sine of 0 over 0, which results in an indeterminate form. Look at that. So what we have to do is, using L'Hospital's rule, L'Hospital stated that if you can't evaluate the limit because of indeterminate form, the next best thing is to evaluate the limit as the derivative of the top function over the derivative of the denominator function, and that will tell you what the limit is going to. So if we do that, simply reapply the limit, but instead of doing it on sine of x over x, we will do it over the derivative of sine of x, which is cosine of x over 1. When we apply the limit, or when we evaluate the limit, we end up getting the quantity 1 over 1, and we're done with evaluating limit because this equals the value of 1. Now what happens if you do this and you get, there are a couple things that could happen. The first thing is you get another indeterminate form. Let's say, for example, you got another 0 over 0. Well, L'Hospital's rule also applies as a stronger form, where you're allowed to apply it to the derivative of the derivative. And if you get the limit to exist at that point, or either become 0 or undefined, you would have the answer to what the original limit would be. So let me try to find an example of that, and I'll be right back. Okay, so here we're back with an example, and we're going to just pretend that we are just going to try to evaluate this limit, and what we find out is when we plug 0 in, we get 1 minus 1 over 0 squared, which gives us indeterminate form. So we're going to go ahead and try our L'Hospital's rule. We're going to take the derivative of the top, which will be negative sine of x over 2x. We reapply the limit, and we get negative 0 over 0 again, which is indeterminate. So now we're going to use a stronger form of L'Hospital's rule, which says to just take the next derivative of the top and the bottom, go through the same process, and we end up getting negative cosine of x over 2, and when we plug the value in for the limit, we get negative 1 over 2, which this would be the value of our original limit. So once we get a value that works, whether it be an actual numerical value of 1 or 0, or even if we got 1 over 0, that would be considered to be an undefined limit. So our answer for this problem is negative 1/2. But notice this time we had to do L'Hospital's rule twice. Okay, so I think we're back, and I found an example that I could use, and I have the limit as x goes to 0 from the right, because remember the cotangent function, it has a behavior where it's a decreasing function, and as you approach 0 from the right, you're heading to infinity. And the other function x will be going to 0. So you'll have this indeterminate form of 0 times infinity, which we can't really, it's indeterminate, but we can't just plug in L'Hopital's rule. To use L'Hopital's rule, you have to have this in a quotient form. So the first step is to convert this to a quotient form. So what I'm going to do is I'm going to just change this to x over the tangent of x. Or as some people would say to do, just in case you don't have the reciprocal function, you would do x over 1 over tan of x, and you would reapply the limit. But since I do have a reciprocal form, I'm going to just, before I apply the limit, I'm just going to say x goes 0 from the right of x over the tangent of x. And now when I reapply the limit, I just want to make sure that's still indeterminate, so when I plug in 0 for x, I get 0, and when I plug in 0 for tangent, I get 0 as well. So now I still have an indeterminate form, and this is really just a check to make sure I didn't mess up the function or do the algebra incorrectly. I want to just double check to make sure I still have the indeterminate form of either 0 over 0 or infinity over infinity, and now I can do L'Hopital's rule. So when I do that, the derivative of the numerator is 1 and the derivative of the tangent is secant squared of x, and when I plug in my 0 value for the limit, I end up getting a value of 1 over 1, which, when I verify this with a graphing calculator, is correct. As x approaches 0 from the right, the function of x times cotangent of x does approach the value of, it does head to the value of 1. Okay guys, I have one more example to show you with indeterminate forms, and this one is probably one of the more interesting ones of using L'Hopital's rule. In pre-calc, you may have learned that the compounding interest formula is the amount of money at time t is equal to the principal that you start with times 1 plus the interest rate over the n number of compounding periods to the n times t. That is for discrete compounding, where you know the number of times per year that the interest will be compounded. Well, one of the things that we suggest in pre-calc is that as n approaches infinity, you move towards the Pert equation, which is the amount of money is equal to the principal times the exponential number to the RT. Now this is kind of mysterious, and a lot of people may wonder, well, why do we switch over, and why is E the constant? And since we know L'Hopital's rule, we can now prove this. So what I intend to do is show how these two components are equal as n goes to infinity. So what I'm going to do is I'm going to set out to just do the limit as n goes to infinity of 1 plus r over n to the n power, and as n goes to infinity, that will equal e to the r. So let's see how we're going to start this off. I'm first going to start off by stating that f is equal to 1 plus r over n to the n power. And then I'm going to do the limit on, I'm going to limit n to be driven to infinity. Now, in order to do this, I will look at what the limit is, because I first should plug in infinity and see what I get for the limit. And when I do that, I get 1 plus r over infinity to the infinite power, and that is an indeterminate form because it's 1 raised to the infinity. So that tells me I've got to use L'Hopital's rule, but I've got to change the form first. So what I'm going to do to change the form is I'm going to use a logarithm on each side, and when I do that, the power comes down in front of the natural logarithm, and I'm just going to bring the limit outside because I can change the order of my limit. So now I have the limit as n goes to infinity of the natural log of 1 plus r over n, the n, not to the n power anymore because I brought the n exponent down, and that equals ln of f. So now I'm going to just check this to see if I still have an indeterminate form, and when I plug in infinity, I have infinity times the ln of 1, which is also infinity times 0, which is still indeterminate. So now I just have to change the form to a 0 over 0 indeterminate or an infinity over infinity indeterminate. So what I do is I just say the natural log of f is equal to, and I'm going to have natural log of 1 plus r over n. Let me make sure that looks like an r, over 1 divided by n. When I check the limit again, I should see that I have a 0 over 0 indeterminate form, and the natural log of 1 over 1 over 0, 1 over infinity, gives me a 0 over 0 indeterminate form, which now allows me to use L'Hopital's rule. L'Hopital's rule says to take the derivative of the top, which is 1 divided by 1 plus r over n. Don't forget the chain rule, negative r over n squared, divided by the derivative of the bottom, which is negative 1 over n squared. Hopefully you can see at this point that the n squareds will cancel, the negatives cancel, and now I'm going to reevaluate my limit of 1 over 1 plus r over n times r. Well, the limit becomes 1 over 1 times r, and that's equal to the ln of my original function that I started with. So I really want to find out what f is equal to, and if the ln of f is equal to r, then that implies that f must be equal to e to the r, hence proving what I set out to do before, saying that the amount equation becomes the Pert equation if n is driven to an infinite number of compounding cycles, and that's called continuous compounding. So hopefully through this exercise I've shown you how to do another L'Hopital's rule with an indeterminate form, and also answered the mystery of why this equation becomes this equation in pre-calculus, and now we know enough math to actually explain why it becomes the Pert equation.